Today, let's look at section 4.4, which is a brand new topic, the topic of complex numbers or imaginary numbers. So far, we've only discussed real numbers, right? We've seen integers, we've seen fractions, we've seen whole numbers, we've seen irrational numbers, but they've all been real. Now let's talk imaginary numbers. And an imaginary number was created so that we could solve problems with negative square roots. Okay, so the square root of -1 is what we call I. Whenever you see an I, you're going to just leave it exactly as I. However, when we have powers of I, we want to simplify that. So for example, I squared is really the same thing as the square root of -1 squared, right? I squared, I is the square root of -1, and squared means we would cancel out that square root and we're left with -1. So I squared is -1. I to the third, okay, I to the third is the same thing as I times I squared. Well, I is simply I, but I squared we just said is -1. So I times -1 is -I. So I to the third is -I. Now, what if we did I to the fourth? Well, I to the fourth we could write as the same thing as I squared, all squared, right? So let me just erase that so I have room. I to the fourth is the same thing as I squared, squared. Well, we said I squared is -1, so -1 squared gives me +1. Okay? These four you want to have memorized. I to the first is simply I. I squared is -1. I to the third is -I, and I to the fourth is 1, based on the fact that I is the square root of -1. What happens as the powers get larger and larger? Well, the good news is it just repeats. Remember, if I to the fourth is 1, anytime we can put I to the fourth into the exponent, it'll have a multiple power of 1. So for example, I to the fifth is the exact same thing as I times I to the fourth. I is I, but I to the fourth we said is 1. So I times 1 is I. So notice we just came back to the beginning. I to the sixth is the same thing as I squared times I to the fourth, right? When we multiply, we add exponents. So we have I squared times 1, because I to the fourth is 1. But recall, what is I squared? I squared is -1. So the pattern continues by the cycle of 4. That means 4 goes into 7 once with 3 left over. So this is the same thing as I to the third, which is -I. I to the eighth, 4 goes into 8 twice. So it's really saying I to the fourth times I to the fourth, which is 1 times 1 is 1. If we continue with this pattern for any higher order, we can find our solutions. So for example, when it says I to the 26th, I think about how many times I to the fourth can go into that power. So I'll write it out in 2 ways. I to the 26th is the same thing as I to the fourth times 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 I to the fourth. That would be 4 plus 4 plus 4 plus 4 plus 4 plus 4 is 24. So I would need 2 more to make 26. Remember, I to the fourths are all ones. So all I care about is what I squared is, and I squared is -1. So this answer will simply be -1. The other thing to look at is, again, the power of 4. So 4 goes into 26 6 times with a remainder of 2. We're going to focus on that remainder of 2, which tells us I to the 26 equals I squared, whatever that remainder is. And as we saw, I squared is -1. Okay, so again, please make sure you have these first four memorized. I to the first is I squared is -1, I to the third is -I, and I to the fourth is +1. So now let's simplify some square roots in terms of I. So for our first one here, I'm simply going to break this down to -5 is the same thing as -1 times 5. Whenever I see that negative inside a square root, I'm going to know that an I needs to get pulled out. And that's because, again, it's really a square root of -1. So the square root of -1 is I. That comes out. And then the square root of 5, we can't do, so that stays in. So there's my simplified solution. For part B, we have a negative out front, and then -64 is the same thing as -1 times 64. What happens here? Well, we have a negative out front. Let's not forget that. The square root of -1 is an I comes out front, and then the square root of 64 is 8. So that comes out front, and then there's nothing left in the radical. Clean that up. That gives me -8I is my answer. Recall, the only reason that this is negative is because there was a negative out front. You try simplifying C. Now let's look at multiplying. Okay, I'm going to do all of these with you. So when we're multiplying, it's super important that we simplify each radical first. I can't emphasize that enough. If you don't, half the time, your sign is going to be wrong. Okay? Then after we do that, we multiply radicals like normal. Remember when we multiply radicals, outside with outside, inside with inside. And then simplify at the end if needed. So our first one's really straightforward. We have 18I times 3. So 18I times 3, simply just multiply those real parts, the coefficients of the values. So 18 times 3 gives me 54. And there's no other i's, so the I stays as is. For part B, we have to simplify this first, okay? This square root of -7 can be simplified. So we have an I out front, but the square root of -7 is really -1 times 7. So now if I simplify this, the square root of -1 is an I. So now out front, I have the I to begin with and an I that I just pulled out from the square root of -1. I can't take the square root of 7, so that stays as is. Once I've simplified, now we can multiply the parts on the outside and then the parts with radicals. So I'm going to first multiply I times 2I, and that would give me 2I to the third. And then root 7 is the only radical, so that stays as is. At this point, we need to simplify. Remember, I don't want to leave I to the third as is. If I go back up to my chart here, I to the third is the same thing as -I. So I'll write this as 2 times -I root 7, and then just clean that up. That becomes -2I root 7. Okay? For part C, why don't you try that one on your own? Please remember to first simplify the radicals before combining them. Give that one a shot, and we'll make sure to talk about it tomorrow. D. For D, what we need to do is just simply use our exponent rules. When I multiply, we add exponents. So this becomes I to the 3 plus 7, right? So I to the 10th. But this is a higher power of I, so we don't want to leave it like that. We want to simplify. So the trick is to say, okay, how many times does 4, because I to the 4th is 1, how many times does 4 go into 10? 4 goes into 10 twice with a remainder of 2. That remainder is what's important. It's saying I to the 10th is the same thing as I squared, and I squared we found is -1. Okay, so go back to make sure you do C. All right, so we were just looking at imaginary numbers. Now let's talk about complex numbers. Complex number is very similar, but instead it's made up of two parts, a real part and an imaginary part. Okay, so as we can see, 8i, -4i, I root 5, all of those were just made up with an imaginary part, so that's a pure imaginary number. A plus bi is a complex number because a is the real part and bi is the imaginary part. So when we perform operations, the real parts usually go together and the imaginary parts go together. So on A, very straightforward when we're adding, both of these are imaginary parts. So we'll just combine them together and I get 16i. Just like when I'm adding with x and y, only the coefficient changes, okay? I plus I does not make I squared. So only the coefficient changes and we're left with a pure imaginary number. If I do B, these are two complex numbers. So notice -5 is the real part and 2 is the real part. And if I take a different color, +6i is an imaginary part and -11i is also an imaginary part. So when I add them together, I want to make sure I'm combining those like terms. So -5 and 2 makes -3, and 6i and -11i makes -5i. And there you have it. You try C, make sure to distribute the negative sign. Dividing imaginary numbers. When I'm dividing imaginary numbers, what we need to remember is that I is really the square root of -1. And we never want radicals in the denominator. So what that means is that we cannot have i's in the denominator because an I is the square root of -1. So we have to clear that. Okay, when there's just one term, it's very straightforward. When there's two terms, we have to use something called the complex conjugate. So the complex conjugate means that if I have a complex number a plus bi, then I need to multiply by a minus bi. So just the middle term changes signs. When we multiply those, because the operations are opposites, it'll cancel out all of the imaginary parts. So what happens when two conjugates are multiplied together? The imaginary parts will cancel. Okay, if they haven't canceled, something went wrong. So let's look at when there's just a pure imaginary number in the denominator and when there's a complex number. So for A, there's just a pure imaginary. So I don't need to use the conjugate. What I need to do is just get rid of I. Well, if we go back to the very beginning, remember, I squared, and I'll star this for now and then we'll come back, I squared and I to the 4th created integers that are no longer imaginaries. The i's are gone. So if I can create denominators that either say I squared or I to the 4th, I know we'll have -1 or 1, and the imaginary part has completely disappeared. So that's going to be my goal when I have an imaginary part in the denominator. Okay, I want to make this I become an I squared. So what do I have to do? I just multiply it by I. If I do that on the bottom, I must do it up top. So now the top becomes 9i plus 3i squared, and the bottom becomes 2i squared. Recall that we just said I squared is the same thing as -1. So I can substitute -1 wherever I see I squared. From here, I'll clean that up. That's saying 9i minus 3 all over -2. Now, there's a couple things to do. Now that we've simplified, a couple things to do so that this is written in a nice way. Whenever we're writing complex numbers, we always have the real part come first. So I want to have the 9i part come second. The other thing is that we never really like to have negatives on the bottom. So if I was just to clear the negatives, I'd bring that negative up top. So it would be negative 9i and now a positive 3 and a positive 2 on the bottom. But again, I want that I part to come second. So I'll switch this so it says 3 minus 9i all over 2. And we can't divide anything by 2, so there's my answer. Okay? Let's look at B before I have you try C on your own. So B has 2 parts to the denominator, which means it's a complex number. When it's a complex number, we need to use the complex conjugate. So I'll multiply by 1 plus I. When I do that up top, we just have to FOIL. So negative 5 times 1 is negative 5, minus 5i, plus 9i, plus 9i squared. In the denominator, we get 1 times 1, we get positive I, then negative I, and then negative I squared. What's the whole goal of using the conjugate? To clear the imaginaries. Let's see if that happens. So I'll clean things up. In the numerator, I have negative 5 plus 4i plus 9i squared. And in the denominator, we have 1, I and negative I cancel, and I have minus I squared. Did the imaginaries cancel? In fact, they did, because even though I still see an I, recall, I squared is negative 1. So I'm going to substitute that in. I now have negative 5 plus 4i plus 9 times negative 1, because I squared is negative 1. And then in my denominator, I have 1 minus, again, I squared is negative 1. When I clean that all up, I have a negative 5 and negative 9 makes negative 14. And notice I'm putting the real part first. Just going to make that a little smaller though. So I get negative 14 and then plus 4i. And 1 minus negative 1 is really 1 plus 1, which is 2. Notice everything in my numerator is divisible by that denominator of 2. So I can divide this to say negative 7 plus 2i. And there's my answer. If only the 14 was divisible by 2, then I would leave it as is. All right, you give C a try using the complex conjugate. Now that we've tried all of our operations, let's look at a few scenarios when we have equations with complex numbers. So, for part A, when I'm solving for x squared here, I'm just going to subtract 7, and now I have x squared equals negative 4. I would then take the square root. Remember, when you take a square root, you need the plus or minus. That's really important. But I'm not going to leave it like that. And I'm also not going to say no real solution. I now know that when I have a negative inside, it really just means an I comes out. So I have plus or minus, an I comes out, and the square root of 4 is 2, so x equals plus or minus 2i. You try B. I will give you a little hint, though, that you will have to rationalize. So we'll see how you remember your radical skills. Okay, so give that one a shot. The last type of equation is when we have 2 equal complex numbers, and we want to solve for unknown variables. When we do that, we set the real part with the real part, and the imaginary part with the imaginary part. So notice A will go with C, and then the imaginary part, I can just get rid of the I's even. B will go with D. So I'll do the second one for us. In this case, the real part on my first side of the equation is 3x plus 1, and the real part on the second equation is 2x. So I'm going to set those equal to each other. 3x plus 1 equals 2x. Then I'm going to set the imaginary parts equal. So y plus 2 is attached to the I, and 2y is attached to the I. So I will set those equal to each other. Now I'll go ahead and solve both scenarios here. I will subtract 3x, so x equals -1. And then I will subtract y, so y equals 2. All right, go ahead and give A a shot. Once you have done that, I want you to practice some more operations with these imaginary numbers. Perform the operation and then please make sure to simplify. You should never have a power of I greater than 1. Good luck!